Hello everybody. So today I'm going to talk about one of the main projects I have been working during my time as a research fellow here at the University of Auckland. Now, this particular problem is actually motivated from an experimental device, which is being designed and manufactured by Dr. Alejandro Giacomotti and his group at the C2N in France. This group are our collaborators. We're working alongside them. And this particular experiment are related to two couple photonic crystal nanocavities, which I'm just showing you here on the right. Now, for the people who may not know, a photonic crystal, you can imagine that it's a thin layer of indium phosphide where you drill holes in a periodic fashion. Now, if you drill holes in a proper way, you can actually change the optical properties of the device, and you can actually make photonic insulators out of them. What I mean by that is that if you were to pump light into the thin layer of indium phosphide, then the light will be reflected. Now, this setup is quite powerful, at least in an experimental setting, because now you can imagine that you can take holes away, and if you take holes away, then you can create a plethora of new optical devices like waveguides and cavities. Now, for today, I'm going to talk about two couple nanocavities, which as I told you before, I'm showing you here on the right. Now, in this particular setup, we take holes and in these two regions, and those two holes, when we take holes out of these two regions, we create a defect. So we create two defects or two cavities. And the interesting thing about these cavities is that if you were to pump light into the device, then light will be actually trapped in these particular defects on these two cavities. And due to the separation between the cavities, you actually have two resonators of light that are actually coupled. All right, and this is basically the idea. So if I were to pump light gets trapped in these cavities, and because of their separation, they basically are two reservoirs of light that are coupled. Now, these devices are quite interesting because they are really, really small. We are talking about holes with radiuses of the order of nanometers, and because of that, they actually operate with a low number of photons. This is actually quite interesting because a lot of people in the quantum optical community see this experimental setup as a possible experimental realization of a fundamental quantum optical model called the two-side Bose-Hubbard dimer model. Now, our contribution in this particular project was to actually try to understand what kind of behaviors one would expect if we could actually, from this device. Basically, if I were to pump light, we would like to see if we were to measure the amount of light trapped in cavity A and cavity B, we want to see if we can find actually interesting dynamics emanating from that. For that purposes, we take this quantum optical model, which can be quite complicated, and we start actually studying the semiclassical approximation. What I mean by that is like this quantum optical model, you can actually, following this algorithm, you can actually derive this system of ODEs, and this system of ODEs will become valid in the thermodynamic limit. What I mean by that is that as the number of photons increases in this cavity, my system of ODEs will actually describe more properly the functioning of this particular device. Now, here, what I'm showing you here are the two system of differential equations. This is a two-dimensional complex system of differential equations, or you can see it also as a four-dimensional real vector field. Now, here A represents the light field trapped in cavity A, which I call cavity A, and then B will be the light field that is actually trapped in my other cavity. Now, the setup that Alejandro's group was actually interested in with this particular device was that the case where you actually pump the same amount of light to the two cavities, and the two cavities are manufactured in such a way that they are identical, right? So basically, we have the situation where we are pumping with certain intensity, with the same intensity, both cavities, and these cavities are manufactured in such a way that their detuning with respect of the input signal is the same. And you can imagine now that depending on a particular device, then you're going to have a particular level of coupling. Now, as you can see in this particular setup, we have a symmetrical case, and what we're going to have is a system of differential equations that are C2 equivariant, or basically they are symmetric on the permutations of A and B. Now, so just to more or less kind of summarize at least our experimental motivation is that now we want to use this semiclassical approximation, and we want to understand for a fixed coupling kappa, that means for a particular device that they can manufacture, what kind of dynamics can be actually observed as I change the detuning and the injection amplitude. Now, in particularly for the detuning and this injection amplitude, these two parameters are things that they can change in a particular experiment. So basically, they don't need to change the photonic crystal, so they can actually do it really easily. Now, whenever we observe any kind of interesting dynamics, and this is also another part of our work, we also want to understand how these relate back to experimental data that they can actually observe, and also how can actually relate back to the quantum optical model. All right. Now, this is the experimental motivation, but at least for this talk, I want to give another mathematical motivation. And this one here, I'm just going to motivate this talk in the following way. So here, I'm just showing you a parameter plane. Here we have our injection amplitude F. We have our detuning delta. Then we're going to fix our complete certain value kappa is equals to 2. All right. Now, if I were to pick F and delta in such a way that I'm on this blue star, and I pick initial conditions and I simulate my system of differential equations, what I'm going to see is the following. I'm going to have the case where I have two chaotic attractors that are isolated. Now, these two chaotic attractors are quite interesting. Here, the one that I'm showing you here, or I'm circling here on red, showcases a situation where one of my cavities has more light than the other one. So here I'm just showing you temporal traces of the intensity. So you can imagine that in this particular situation, this chaotic attractor, or in this particular setup, I'm pumping light to my cavities, and then one cavity is actually gonna contain more light than the other one. And then, and even though I'm symmetrically pumping them, let's say the stable case is one cavity having more light than the other one, and the amount of light that this one is trapping is actually chaotic, right? So it's oscillating back and forth, but at all times, one cavity is always going to win. All right. Now, due to the C2 equivariance properties of my system, then because it's an asymmetric chaotic attractor, then you have another situation, which now I would like to present in. You have another chaotic attractor related by the group action of permutating my two light fields, where you have the opposite situation, where you have now one cavity, the other cavity that was losing, now winning. So depending on which initial conditions I start from, I can actually end up in a situation where one cavity is winning over the other one, but it's winning in a chaotic way. Now, this is interesting. However, if I change a little bit my parameter values, and then I'm showing you over here, now what I observe is going to be something different. What I'm going to observe here now is that now my two isolated chaotic attractors, they're actually merged. All right, and then I have the following situation. I have a situation where, yes, we have a chaotic attractor again, but now the periods where one cavity is winning over the other one is actually changing in unpredictable times, right? So before we have a situation where cavity A or cavity B was always winning. Now in this particular case, we're just chaotically switching between these two cases. So we don't know which one is winning at a particular time. Oh, sorry, whoever is winning is actually going to change at unpredictable times. So, and maybe this is the question that I want to motivate this talk, at least in a mathematical level, is what are the geometrical mechanisms that actually can help us understand why these transitions occurs in the first place? So basically, what kind of bifurcation we can is actually responsible for this symmetry increasing of chaotic attractors. All right. Now, as a clue, because you have to start somewhere, right? What we are able to find is that close nearby to these parameter values that I was choosing, we can actually find a clinical bifurcation, which I'm just showing you here as a gray curve. And along this curve, my system exists, but it's called a C2 equivalent clinical bifurcation. So for example, if I pick a point along this curve, I'm going to have the following situation. I'm going to have a biasymptotic solution to a saddle equilibria, which I'm showing you here. So I have a solution that converges backwards in time and forwards in time to a symmetric equilibrium of a saddle type. And this solution, or this biasymptotic solution, is asymmetric. So basically by this group action, by permutating my sites, I can actually get another homoclinic. So basically we have a situation where we have two Cherenkov orbits converging to a symmetric equilibrium. and in this case, I'm going to call P. Now, in this particular setup, and this is something just to emphasize here, P is going to be a symmetric equilibria where the light field A and B are going to be the same. For the people, for the experts in the audience, this means that P lies in the fixed point subspace of my system of differential equation. And this particular fixed equilibrium point has a three-dimensional stable and a one-dimensional unstable manifold. Now, what I'm showing you here are basically, as a first portrait, is basically the unstable manifold, or one-dimensional stable manifold, leaving this equilibrium point and then converging again in forward sign back to the equilibrium. Now, you can imagine that this is a one-dimensional curve, so a one-dimensional manifold, and this is going to be Hispana, or the other part of the other curve that forms this one-dimensional unstable manifold. And now you can imagine that there is also a three-dimensional stable manifold, which I cannot show and I cannot illustrate because, well, computers are planar. Well, one day when we have holograms, maybe I can show something like this. You have a three-dimensional manifold that basically separates which initial conditions go to which situation, all right? If I go in a situation where B wins or in a situation where A wins, right? Now that we know that we have this kind of Cherenkov bifurcation, we can actually identify that this Cherenkov bifurcation is of a wild case. So basically, we check the eigenvalues of my saddle equilibrium P. We can see there is a wild Cherenkov bifurcation, so there should be exist infinitely many Cherenkov bifurcations occurring nearby. So what we can do is basically, or we can actually use this fact and apply certain techniques that have been developed by Roberto Barrio, Andrei Chilnikov, and Leonid Chilnikov. And these techniques are based on defining a needing invariant in this kind of system of differential equations that are C2 equivariant, and that they exhibit this C2 equivariant Cherenkov bifurcations. And the idea with this needing invariant is that what we're going to do is that we're going to pick parameter values. Just showing you, maybe starting from this situation over here on the right. I'm choosing parameter values, for example, delta and F. I take the unstable manifold on my saddle equilibrium point, and then I'm starting to compute these maximas and these minimas. So here I'm just marking the maximas, and here's certain minimas. Here I'm just showing you a temporal trace of how it looks. And the idea is like whenever I get a maxima, I give up. I can translate a maxima and give it a tag or a symbol. I say, you get a plus. Then our next one is another maxima, so I give it another plus. Then we get a minima, then I give a minus, and then the next one is another minima, so I give it another minus, and then after a while it just goes always plus plus plus. So I basically just say, all right, so this sequence associated with this unstable manifold for these parameter values is one where you have a tails of just plus. Now, the interesting thing is like if you change your parameter values and you do the same game, then you will have a different sequence. In this particular case, I get a plus, and then I get a lot of minuses, right? I get a tail of minuses. And the nice thing about this kind of approach is like now you can imagine that I can do a grid on my parameter plane, and then I can compute this needing sequence, and given a different given a sequence, then I can assign a color. All right. And the idea is whenever there is a change in color, it will imply that there must be a bifurcation, or there must be a topological change that allows this needing sequence to change. Now, if we were to do this, and this is what I'm showing you just now, what I'm going to get is this kind of colorful picture, right? Now, what you need to understand in this colorful figure is that whenever there is a change in color, it means that my needing sequence has changed. All right. Now, the interesting thing about this particular situation, and which I want to emphasize here over here, is that here I have my case where my two chaotic attractors were isolated, and then here I have my situation when they are actually merging. All right. So these already tell us something, right? That maybe, right, the situation where these chaotic attractors are merging, one can see the situation also in the situation. One can also see this situation as one case where my system is allowed to have Cherenkov bifurcations. So you can imagine all these colors over here represents a bunch of Cherenkov bifurcations. And you can see over here that is a high that basically separates the moment that I get a solid red to this colorful color. And then on the side, I also see a kind of sharp change, right, that allows this kind of transition to occur. All right. Now, this kind of figure was computed using these parameter shaping techniques. But here at Auckland, at the University of Auckland, we specialize on basically two-point continuations of two-point boundary problems, or basically how can we compute codimension-one bifurcations by finding and computing the intersection between several and several manifold, right? So in this way, now that we have these techniques, now the next step that we wanted to do is like, can we actually find the geometrical objects that can actually tell us why is this occurring? So here I'm just showing you here again the situation where we have our chaotic attractors that are isolated. What we were able to do is like we can actually find out that these chaotic attractors are being, let's say, trapped, or they're really lying close to the unstable manifold or two subtle periodic orbits, right? Gamma naught, which is asymmetric, which I'm showing you here. And because it's an asymmetric periodic orbit, you're also going to have a panel, which we're going to call here gamma naught asterisk. Now, these subtle periodic orbits are kind of interesting because if you compute their stable and unstable manifold, you're going to find that this particular subtle periodic orbits, they're going to have a three-dimensional stable manifold and a two-dimensional unstable manifold. Not only that, what we also find is that the chaotic attractor is actually contained in the closure of these unstable manifolds, right? So you can imagine, and this is what I'm showing you here in the orange surface. So the orange surface here shows the unstable manifold of this of gamma naught. This is numerically computed. This is no illustration. So what we can do is like, we can actually show is that this unstable manifold, the chaotic attractor is actually going to lie really close to this unstable manifold, and his partner, this other isolated one, is also going to be contained now by the other unstable manifold, which I'm presenting on red. And then we have this subtle equilibrium point, which is just chilling over there up to now. However, if I go back to the situation where my two chaotic attractors are actually merged, now the situation is a little bit different. Now here, if I compute the unstable manifold of gamma naught, you can see right away that before it was isolated, now it actually is allowed to move to the other side of my phase space. And not only that, you can actually see, and this is what I'm showing you here, you actually can see some curves that actually connect the subtle periodic orbits with my subtle equilibrium P. So basically what I'm showing you here is a situation where I have a connecting orbit that converges backwards in time to gamma naught, and it converges forwards in time to P. So basically here, you can imagine that I'm showing you the moment when the three-dimensional stable manifold of my subtle equilibrium P is intersecting transversally the two-dimensional manifold of my subtle periodic orbit gamma naught. Now, this is quite good because it means that at one point, these two manifolds have to intersect for the first time. So basically, they have to intersect tangentially. And then by setting up a suitable two-point boundary problem that we actually developed, we can actually find the moment when these two manifolds are actually intersecting tangentially, which is the situation that I'm just showing you here on blue, which is the curve that I'm going to call F. So you can imagine that at this moment, whenever I'm on top of this curve, my stable manifold of the subtle equilibrium P and the unstable manifold of my subtle periodic orbit gamma naught are going to intersect for the first time. And indeed, this is the case. If I were to pick a point along this curve, what you're going to see is the following. I'm going to actually see a tangency bifurcation, which is connecting gamma naught to P, and we have the other connection from gamma naught asterisk to P, given by the two equivalence of our system. Now, this particular situation just showcases you the first moment where these two chaotics are actually going to start merging. All right. So this is kind of nice. It's like, all right, we get one bound, right? We get the height of this colorful figure. The question is, what about this other side, right? What about the side that goes over here? What is the bifurcation that explains that? And in particular, we can actually identify which is the bifurcation that it is. And in this particular case, it's going to represent a connection between the unstable manifold of my subtle equilibrium P and my subtle and the subtle periodic orbit gamma naught. Now, in this particular case, what we have is that the unstable manifold, which is one-dimensional of my subtle equilibrium P, is actually intersecting the three-dimensional stable manifold of my saddle periodic gamma naught. So basically, I have a bisymptotic solution that converges backwards in time to my symmetric equilibrium P, and converges forwards in time to my saddle periodic orbit gamma naught. Now, this is kind of interesting. And the reason why this occurs, and there is one can say, or the intuition why this occurs is the following. Gamma naught is a three-dimensional manifold, and in particular, is an orientable three-dimensional stable manifold of this periodic orbit. And basically, you can imagine there is a cylinder that is separating my phase space in an inside and outside. So basically, you can be inside the cylinder and outside the cylinder. All right. So basically, whenever I am in the red region, so basically, whenever I'm in this region over here, you can imagine that my unstable manifold is inside my cylinder. All right. So basically, it's going, in this particular case, it's going to be attracted to in this particular case, asymmetric steady state. But then at one point, this unstable manifold intersects this cylinder, this three-dimensional cylinder, and then it's allowed to go to the exterior. Now, whenever it moves to the exterior, what is going to happen is like he's allowed to interact with anything that is outside this exterior, and voila, what is outside this, or what is outside of this exterior of this hypercylinder? Well, it's going to be the stable manifold of my stereo equilibrium P. And why is that? Well, because we are already below F. So because we are already below F, we have this transversal intersection between the stable manifold of P and the two-dimensional unstable manifold of gamma naught. And then because of the lambda lemma, and this is a consequence of the lambda lemma, that will imply that the stable manifold of P is actually accumulating in the three-dimensional stable manifold of gamma naught. All right. And this is kind of interesting because now we have a beautiful situation, right? Like we have the two bounds, right? But now these two bounds actually intersect in a point. All right. So this is a kind of funny that now we have this point, and what is this point representing? All right, is representing a situation where I have a trajectory, all right, that is leaving P, is converging in forward time to gamma naught, and then from gamma naught, I'm leaving back to P. All right. Now, this part of the strip, the one that connects P to gamma naught, this is a codimension-one bifurcation, while the connection that goes from gamma naught to P is a tangency bifurcation. And this is what is called in the literature a degenerate singular cycle. All right. Now, this is a codimension-two phenomena, and in particular, so it's a really interesting object that has been studied in the literature. Now, just to kind of introduce a really nice representation that we came up to kind of explain the situation here, I'm showing you here the same connection or the same cycle, but in what we call a compact defined time connection plot, or CTC plot in short. And basically, this is a particular type of plot that we just made up or just created just to be able to explain these kind of connections. So what you can imagine in this particular setup is that at every end, so maybe I should go here one more time. Here we're going to have the intensities of my cavity A and my cavity B, and then here as a third variable, we're going to have this T hat, which represents our compactified time. So T hat will represent the following. So whenever I'm at an integer value of T hat, I'm going to put a limiting object, right? What I mean by this is like at T naught is equal to 0, I'm going to put my zero equilibrium P. At T hat equals to 1, I'm going to put my zero periodic gamma naught. And in this particular setting, at T hat equals to 2, I'm going to show P. Now, the nice thing about this projection is that now in the open intervals between these integer values, we're going to actually put our connections, all right? And this is just to illustrate, just give a notice about how the connections are occurring. So in this particular case, I'm leaving P and I go to gamma naught, and then from gamma naught, I'm going to P, and the connection from gamma naught to P is a tangency bifurcation, all right? Now, as I told you before, this particular point has been studied theoretically, and some of the unfoldings have been theorized by these two particular papers, one by Alan Chapman, Vivian Kier, Edgar Knobloch, Alderman and Rademacher, and then there is also this work by Alexander Loos and Alexander Rodriguez, where they have studied the unfolding of this particular point. However, this is the first time, I'm going to show you the first time where this has been actually numerically computed, at least a bifurcation diagram. Now, here I'm just going to go a little bit talk a little bit about other interesting things that we observe on this diagram. As you can see, we have this chaotic attractor over here, but then we have these regions also, and these regions with solid colors, right? Where my needed invariant doesn't change, right? So the question is like, what is actually occurring in these particular points? Now, if I pick parameter values over there and I do the same exercise, what I'm seeing here is that now my solution or my unstable manifold of P is actually going to accumulate in an attracting periodic orbit, in this case, which we call gamma AS. And this attracting periodic orbit is what is called an S invariant periodic orbit. So basically, it's a periodic orbit that is not fixed point symmetric, but it's actually symmetric as a set. So basically, if I apply my my group action and I permute A and B, then I ended up with the same periodic orbit. Now, if I pick another parameter value in the other solid region, what I find is like I still get accumulated to my to this periodic orbit. However, you can see that my transition changes, right? Before I went 2 times. I get a plus, and then I accumulate in this periodic orbit. So basically, I have a needed sequence of plus, minus, plus, minus, plus, minus. And over here, what I get is just 3 pluses. And then I go to a plus, minus, plus, minus. And if I keep going, then what I get is a situation where I get 4 pluses first, and then I go plus, minus, plus, minus, plus, minus. All right. All right. So this is kind of interesting. And the real question that comes next is like, all right, so these are the solid regions. Why did they appear? Why do we just start seeing these kind of objects now? Now, what we did is like, now we take this attracting periodic orbit, we do continuation, and then we can see that it actually goes through a saddle of bifurcation. So it creates, or it disappears with a saddle periodic orbit. And this is kind of interesting because now we have this attracting periodic orbit that disappears with this saddle periodic orbit that is also S invariant. And this saddle periodic orbit is also it also has a 3-dimensional stable manifold. So basically, it also bounces an inside and an outside. And what we can observe is that the codimension-1 heteroclinic bifurcations between P and this saddle periodic orbit actually bound, and these are the ones that are going to bound now the solid regions. So by doing this, now we can see that, all right, the heteroclinic bifurcation that goes to this new saddle periodic orbit. If I pick a point over here, I'm going to have a connection that does plus, plus, and then goes plus, minus, plus, minus. Now, if I pick another point in the other heteroclinic bifurcation, I'm going to get the same situation, but then I'm going to get plus, plus, and then I go plus, minus, and then I keep going like that. All right. So this is kind of nice, right? It just tell us that by inside this heteroclinic bifurcation, we can actually know when my needed invariant actually becomes solid or doesn't change for a while. So basically, when I go back to an attractor. And not only that, and this is the nice, beautiful thing about this work, which we were really excited, they also have a high. And in particular, we can actually find the same, we can actually find the high, and we can identify as also a codimension-1 bifurcation. And it's going to be also a tangency bifurcation. And this tangency bifurcation is going to be between my saddle periodic gamma naught and this new saddle periodic that is S invariant, which I'm going to show you much better with this CTC plot. So what I'm trying to say here, and this is the situation here on this particular point here, is that I'm going to have a trajectory that leaves P, goes to gamma naught. Now, this part of the connection between gamma naught and gamma naught S, right? This is going to be a tangential bifurcation between the 3-dimensional stable manifold of gamma naught S and the 2-dimensional stable manifold of gamma naught. And then after a while, I'm going to get a connection back from this gamma naught S to P. Now, the interesting thing about this connection is that the last bit of my trip, the third one, is structurally stable, which means that the 2-dimensional unstable manifold of this gamma naught S is actually intersecting transversally the stable manifold of P. And what we see here is like the middle part of this strip actually is tangent. And this particular situation is the one that actually explains the height of my E to P connections, right? And this is what we observe with our numerical approach, and we have numerical evidence on that. And what we're observing here is like a generalization of these degenerate singular cycles, where we have this chain where we can connect from P to back to P, but then I have this kind of path in between. And depending on which or where the path was the weakest one, we can actually explain different codimension-one bifurcations in our bifurcation diagram. Now, this hasn't been cited theoretically, and there is obviously a lot of work that would be quite interesting if someone is actually interested in working this in a more theoretical level to actually pursue, actually trying to find an analytical unfolding of this particular situation. But at least our numerical data or numerical work actually shows that this particular tangency bifurcation delimit the height of the E2P connections. And the nice thing that I want to stress a little bit more is like, even though we have solid regions, this doesn't mean that we cannot have also furthermore bifurcations. What I'm showing you here on yellow is a symmetry breaking bifurcation of this periodic orbit that is acting and that is symmetric. And what we can see is that this periodic orbit that is attracting symmetry breaks into two asymmetric attracting periodic orbits. And these two asymmetric periodic orbits actually go to a period doubling cascade, which I'm showing you here on red. And then they can actually create a chaotic attractor, two chaotic attractors, which are isolated, but then they also go to a symmetry increasing bifurcation. And this is what I'm showing you here. So even though we are in the solid region, we can still see chaotic attractor or chaotic behavior, but then this chaotic behavior is a little bit different than the one that I showed you before. Here, what you can see is that the height of my temporal traces are changing, but then at every time, or let's say after one oscillation, the intensity of my lights are actually changing quite regularly. So we call this regular chaotic switching. Now, the interesting thing about this is that if we change a little bit our parameter values and we go back to this funny region with a lot of colors, we find like a combination between this regular switching with the other chaotic switching that we were seeing before. Like basically we have periods where things behave regularly, but then we also have periods where things are concentrating in one cavity for a certain amount of time. So we have like this kind of boundary crisis. So the interesting thing about this object, and maybe as a general message that I want to do with this, is that we can actually compute everything. And this is basically what I'm going to say. We can actually, by using these ideas of finding this tangency bifurcation between these three-dimensional stables and two-dimensional unstable manifold, we can actually explain heights of heteroclinic bifurcations in parameter plane. We can actually show boundary crisis of chaotic attractors, inner boundary crisis, and so on. And obviously, I don't want to go into detail because it obviously would be too much information. I don't want to get people a little bit crazy with this. But the point is like, or the message that I want to say is that we can do this, and it's really interesting. Now, and things are not that easy as so at one point you will think that, oh look, this is amazing, you found out a lot of stuff, right? So everything is done, and maybe the gist of what I'm going to say next is like, well, no, actually things are more complicated than we believe. Now what I'm showing you here is the same plot as before, but what I did was I took the unstable manifold of my satellite equilibrium P, and then what I did is like I just computed this Lyapunov exponent, right? And so I wanted to see when this unstable manifold was actually being accumulated into a chaotic attractor. All right. Now, what we found out, and this is the bit that we find it really puzzling at one point, is like you can see that there are regions, right, that are quite solid, right? That basically means that we can find chaotic attractors quite reliably by just integrating these unstable manifold. We can see even over here, whenever we get all these other bifurcations that I was telling you, all these other period doubling and so on. You can also see that these curves are actually bounding where these bifurcations are these chaotic attractors exist or just disappears or are not accessible with my unstable manifold. However, there is this spot over here where it's quite spotty. All right, it was quite spotty, and then we found it quite at first glance we thought basically it was just numerical artifacts, but under closer inspection, we actually realized it's actually more complicated. In fact, if we were to integrate on this spotty area, we are going to actually go to a several attracting equilibrium solution or periodic orbit, depending on which attractors there still exist in the system. And the question is why? What exactly what happened over there? And by trying to answer that question, we actually ended up computing the numerical unfolding of this degenerate singular cycle, the one that I was talking the first time. And what I'm showing you here is some of this situation. There is this HT curve, which corresponds to a homoclinic tangency of my saddle periodic orbit. So you can imagine that this curve represents the first time that the stable manifold of my saddle periodic orbit gamma naught intersects its unstable manifold in a tangential way. Now, if we set up the proper two-point boundary problem and then we continue this curve, we get this kind of interesting bifurcation diagram that actually has this particular curve, which is also another tangency bifurcation, that actually separates between the solid and the spotty area. All right, and this was kind of interesting because it means that actually understanding this codimension-two point can actually tell us a lot about this kind of weird transition between the chaotic attractor. And indeed, this is basically the situation I'm talking about. This is what happens if I integrate in my solid area, and this is the situation if I integrate on my spotty area. Now, what I'm showing you here is just basically the unfolding of this general singular cycle, or the way that it was actually shown to be in the paper of Kirk and her collaborators, where they actually unfold this general singular cycle. This is a sketch. Just to explain a little bit about this sketch, or what it means, all this curve, is that here on my where I'm the y-axis, whatever I'm coloring right now red, this represents my E2P connection, or basically the what I call my curve head. And my axis here represents my blue curve, or my F curve. So basically this represents the first time that the unstable manifold of my saddle periodic orbit gamma naught and this stable equilibrium P intersect for the first time. And these curves that they call tip tangency and side tangency are just basically these homoclinic tangency bifurcations that we're computing. All right. Now, this is their numerical, this is their analytical result, where they say, look, things should look like this. Well, and look, and actually no one has actually computed something like this, at least for the different, or no one has seen them, at least on the wild, when studying this kind of system of ordinary differential equations. And what we can do, or what we accomplished in this particular work, was that we can actually compute this particular unfolding numerically. And we can actually show how these objects are actually organized in an explicit four-dimensional system of differential equations. So here is how the bifurcation looks like, close nearby to this codimension-two point, or the general singular cycle point. And here, what I'm showing you is just basically what will happen if I just use a spline and then I just identify my full bifurcation. So I just do a nonlinear transformation in such a way that I can compare this plot more easily with this. And what we can see for this particular case is that actually what we're computing is actually quite damn close to what the theory tells us, right? Which is really amazing, because this is, as I said before, I want to remark, it's the first time that people actually have computed this homoclinic tangency. Now, a little bit to give a little bit of intuition here about what exactly is happening about this homoclinic tangency. What I'm gonna do now is like, I'm gonna move along this particular bifurcation line. So I'm gonna fix my delta value at a certain point, and then I'm gonna start varying my F. So what I'm gonna do now is like, I'm gonna take my homoclinic orbit to my saddle periodic orbit, and I'm gonna see how it interacts with all these folds, all right? How they're moving. So here is what I'm showing you. So I'm just fixing delta, and then by taking this homoclinic orbit to my saddle periodic orbit, I'm just getting this phonic structure that, for the people who have worked on continuation, kind of looks like what one would get, what one could get if you take a periodic solution and then you do continuation, and that periodic solution converges to a Chernigov bifurcation. Now, the situation that I'm showing you here is a quite different one, but it's kind of similar in a sense that whenever I take this homoclinic orbit to my saddle periodic orbit and I do continuation in F, every time it gets a tangency, it falls back again. So it's just moving over here, it's just going back again, and then it moves over here and keep going like that. And then this limiting point is actually gonna be my curve head. And what it means is that, and this is the interesting thing that I'm showing you here, if I were to plot my continuation on my homoclinic orbit at this particular point, I'm gonna get an approximation on my structurally stable heteroclinic cycle. So what I mean by this is like this orbit is approximating to a connection that leaves P, goes to gamma naught, and then from gamma naught goes to P. Now, this side of the connection, the one that goes to gamma naught back to P, is a structurally stable connection because we are below F. And as I told you before, we only don't have one homoclinic orbit, we actually have two. And what we can see is that if you do the same exercise with the other homoclinic orbit that exists in the system, what we are going to get is that it actually going to accumulate in the other heteroclinic cycle that exists in this particular regime. So just to summarize a little bit, just by trying to find, just to try to understand this kind of really weird interplay between chaotic attractors, we actually ended up finding a numerical unfolding of this degenerate singular cycle. Now, this is interesting because it just tells us this, that even though these needle invariant techniques are quite powerful, right? They don't tell us all the story, right? And it's kind of important, and maybe this is something I would like to stress. It's really nice when we can use or combine these two approaches. So we can use this needle invariant just to have a really good idea of what my Cherenkov bifurcations they are. And then you can, with this information, then you can complete your bifurcation diagram just by finding this tangency bifurcation between subtle periodic orbits. Now, what I'm just showing you here is just a situation that goes over here. But then a natural question that some people will ask is like where these curves are actually coming from. And what we can find is that these two particular curves actually come from a peak of Twopoint, which I'm showing you here. And I'm getting another flip bifurcation point that I'm showing you here. So these two codimension-two points are actually explaining how all this tangency and all this heteroclinic bifurcation are actually emanating from. And what we're saying here is just how we actually somehow got this result without us asking for it. We actually got like a numerical unfolding of these particular two codimension-two points and how this unfolding actually interacts whenever you go far away from these two codimension-two points. All right. So in particular, what we found is that the heteroclinic bifurcations and the homoclinic bifurcations come from T, and in particular, we can find the first heteroclinic bifurcation and the last homoclinic bifurcation where Cherenkov bifurcation can exist, which is represented by the cyan surface. And what we can see is that the tangency bifurcation between subtle periodic orbits are actually coming from the flip bifurcation point. All right. Now, what I'm showing you here is just kind of color regions of my parameter plane, where we expect different these dominant chaotic attractors to exist or to lie in our parameter plane. And if you are interested, and obviously this is just to give you a glimpse. Actually, we did quite a lot of stuff, and it will be, if you are interested, and maybe you can think that this can be applied for other techniques, or you are more interested about how much of this can be formalized analytically, I would recommend you to have a look at my paper, or this paper, the 2021, the one discrete and continuous dynamical system, where we went into a lot of details about how this publication actually are explaining all this kind of behavior. Now, just kind of like a final words that I would like to say is that, as I told you when we started this presentation, this work is actually motivated by experiments. And the thing that I wanted to stress here is like these experiments have been carried out. So this is here, basically here I'm just showing you like an experimental bifurcation diagram next to a theoretical one, where some of our predictions are actually being observed. Now, in this particular case, we're just talking about more easy behavior, not the chaotic one. But even though I'm just showing you this, the easy one, what we have shown is like these experiments are being done, and not only that, our results or our analysis are actually being useful to try to understand different dynamical behavior that these photonic crystals can actually exhibit. Obviously, there is more ongoing work. Like right now, Bruno, which is the postdoc that is working and doing the vectorings and experiments on this particular work, he has actually developed, he's actually working more on this experiment just to try to see how much of this chaotic behavior we can observe. And maybe in just that we have the last 5 minutes of this presentation, what I'm just gonna, I don't know, actually, maybe we can leave it over here because it's like 5:50 and some of the people here at Auckland are just gonna be quite tired, and there is a pop time after, so it'd be good to go here. Now, maybe to have a final word over here is that we also have gone more and we actually have checked our analysis, how actually goes back to the quantum optical system. And in particular, we can actually find, and there is something that is also, we have also preprint, we actually have found that this semiclassical approximation actually is quite useful to actually tell us really interesting behavior that we can actually observe also in the quantum optical system. And not only that, we are into this kind of really interesting question where we are asking ourselves, right, now that we can see chaos or really interesting chaotic behavior in the semiclassical approximation, now the question is, how is this chaotic behavior actually relates back to the quantum system? Do we have something like what, quantum chaos or what? So how these objects are actually relating back to each other? And this is something that also is ongoing work, and this is something that we want to push in the future on this direction. And maybe with this, I want to finish the talk. So thank you very much. All right.